Hello. Our next topic in Unit 2, Gases, is Dalton's law of partial pressures, and we're going to show how to apply this law when we have mixtures of gases. First, let's consider this sentence right here. When two or more gases are in a container, each gas behaves as if it occupies the container alone. Okay, what this means is that, or what it means to me is that if you can predict the behavior of a gas in a single container, when you mix that gas with another gas in the same container, the behavior of that gas is going to be identical. And in particular, we're looking at pressures and what contribution that gas makes to the total pressure. So for instance, if we have a vessel here, round bottom flask maybe, and make sure it's capped, maybe with a septum. Okay, and we have two gases. Each dot is going to represent a mole, maybe. And here I have maybe 4 moles of N2 and 2 moles of He, helium. And this vessel has a certain volume. Let's give it a volume of equal to 100 milliliters and a pressure, temperature. Let's make it equal to 290 K. And it has a peak total, okay, a pressure total, but I'm not going to give that a number. Well, the pressure exerted by the N2 gas is the same here as if it was alone. The pressure exerted by N2 gas is same as if it was alone. So basically, if we take the same container and if we can predict what happens if it was alone, just these 4 green dots, then we know what contribution it makes to the total pressure. So again, we could just simply use the same information. Volume equals 1 milliliters, temperature equals 290 K, and this has now a pressure of just for the N2. And we could do the same thing for the helium. I'm not going to draw out all the data, but let me just draw for us the helium, 1, 2, and we can get the P, the pressure exerted by the helium. These are called partial pressures of each individual gas. Partial pressure of nitrogen and partial pressure of helium. Dalton said that if you can figure out what contribution each gas makes to the total pressure, then you have this equation, which is Dalton's law. Dalton's law is simply P total. Now, some textbooks, actually most textbooks, use the summation sign. I literally like to see each gas, but we have either 2 or more gases. So let me give us 3 and put a dot, 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 etc. Partial pressures of A partial pressure of B, partial pressure of C, adds up to the total pressure. Pretty simple, but I think it's quite profound because it says that under the KMT, kinetic molecular theory, and if these gases are acting very close to ideal, then these gases, these green dots don't realize that they're in the same container as these red dots. Sure, they may bounce off of each other, but it doesn't change how these green dots push against the inner walls of the container. Okay, it has no effect. Now, obviously, the total pressure would be more because this has more moles of gas under the same volume temperature conditions. That is Dalton's law. Now, consider the next sentence, which is the partial pressures or the partial pressure of a gas in a mixture is proportional. You could even say it's directly proportional to its mole fraction. Okay, simply a mole fraction is part over whole. How many moles of the gas divided by the total number of gas molecules, or total moles of gas. So let me show you that equation. Pretty simple. First of all, the mole fraction. The mole fraction looks like this. It's a kind of a funny looking X, and let's say the mole fraction of gas A equals the moles of A divided by the total moles. Okay, that's pretty intuitive. Part divided by whole. But what can we use with this mole fraction? Well, if you're able to measure the total pressure here, and you know the mole fraction, then you could get the partial pressures of the component gases. Okay, and that equation is quite simply the partial pressure of A equals the total pressure times the mole fraction of A. You know, if A makes up 50% of the moles in the container, then this number would be 0.5, and it will represent half of the total pressure. So it is directly proportional, and it's based on the number of moles. It's not based off of the molar mass or the volume. Okay, it's based off the number of moles. So that's really it for Dalton's. It's pretty simple, and I have a fairly simple problem that you can do right now. I already worked it out, so let me cover up the answer. You could pause the video and copy the question or the problem, and then unpause it once you have an answer. This is a good test. This represents actually a fairly straightforward problem using Dalton's laws. Okay. About 20 years ago, the FDA approved the use of nitric oxide to treat and prevent lung damage in premature infants. The NO used in hospitals came in cylinders mixed with N2 gas. Calculate the mole fraction of nitric oxide in a 10.00 liter cylinder at 25 degrees Celsius that contains 6.022 moles N2, and in which the total pressure is 14.75 atmospheres. Alright, when you're done with this problem, come back to the video. Okay, I already worked out this problem, and, well, they asked for mole fraction. Calculate the mole fraction. Let me circle that and give it a question mark. But we do have an equation for mole fraction, part divided by whole, and we're worried about the nitric oxide. Now, when you have a mole fraction, maybe you'll be using that to figure out partial pressures, or reverse, if you figure out the partial pressure, you could use it to figure out the mole fraction. So we do have a total pressure. Right now I'm not 100% sure if we need or we should get the partial pressure of nitric oxide. But now that I said it out loud, that we have a total pressure, and we have a volume, and we have a temperature, okay, then that suggests that we should be actually using PV equals nRT, pivnert. Because look at what we have so far in our problem. We have the total pressure, we have the volume, 10.00 liters. We don't know the N total, and we know R, and we have the temperature. So I don't like to rearrange the equation first. I like to plug in the numbers first, then I'll simplify the terms and rearrange the equation if I need to. Alright, so this is quite simple. I do want to warn you that you want to maintain as many significant figures, or at least one more than you think you will have at the very end. So if you think that your sig figs are going to be maybe 3, then make sure that all your calculations give you numbers beyond 3 sig figs, maybe 4 or 5, because you don't want to round yourself. You don't want to round at every step, because you may round yourself out of the correct answer. Alright, so I punched all of this in my calculator and I got n equals 6.02579. I actually did look up the answer because this was from a textbook. The answer would be a little bit different if you used 0.08206 for the R constant, but I always round it to 0.0821. That's your N total. I think that could go right here directly. Okay, yes. And now, since we have the N total and we have the mole of N2, we assume that the rest of that total is coming from NO. So we literally have these two numbers already. Just take the total minus the amount of N2 moles, and we get the amount of NO moles. So it's very, very tiny. Okay, that's why also, you don't want to round excessively, because, if you round it to 0.003, then your answer is likely to be pretty far off. Okay. So this is the part divided by whole, and literally it's these two values, and I get a number 0.000629 mole fraction of nitric oxide. And if I round that, should I round it to 4 sig figs? I get, oh, I didn't round it to 4, I rounded it to 2 sig figs. Why would I do that? Oh, probably because of this 25 degrees Celsius, 2 sig figs. Anyway, that is your answer. 0.0063 mole fraction of nitric oxide. And I just multiplied it by 100% to get the percentage. So it's even less than 0.1% NO. How they packaged it and sent it off to hospitals. So it's, let me do this real quick. Minus 0.06. It's 99.94% by mole percent nitrogen gas and a little bit of nitric oxide. Okay. Alright, so that is a fairly straightforward Dalton's law calculation.